In this chapter, we will discuss the refraction of light when it is incident on a spherical surface. That is, a surface which is a part of a transparent sphere. Let us consider an object placed near a spherical surface of radius r. We want to find the position of image of this object. Medium in which the object is placed has a refractive index equal to μ1, and medium on this side of surface is μ2. A line passing through the object and the center of curvature of the spherical surface is called the principal axis. And for spherical surfaces also, we will use the same Cartesian sign convention that we use for spherical mirrors. So this point will be the origin or the pole, and the direction of incident rays will be considered the positive direction. So any position on this side of pole will be negative, and any position on this side of pole will be positive. So here position of object will be minus u, and radius of curvature of surface will be plus r. This is the same what we would have used for a convex mirror. Now, a ray of light along the principal axis will be perpendicular to the surface and thus will pass undeviated. But one ray is not sufficient to find the position of image. So let us consider one more ray like this. If we draw a normal at this point, then we can say that angle of incidence of this ray will be equal to this term. This ray will undergo refraction at the surface and meet the principal axis as shown. And here this will be the position of image. Here angle of refraction will be given by this equation. Now, using Snell's law, we have this equation. For the rays very close to the axis, these angles will be very small. So we can make these approximations for the paraxial rays. Using these equations, we get this equation. Now, since the angles alpha, beta and gamma will also be very small, so we can approximate them to be equal to these terms. From this triangle, alpha will be equal to this term. Note that we will use all the positions with proper signs, so that the derived equation is general and is valid for all cases. From this triangle, beta will be equal to this term. From this triangle, gamma will be equal to this term. Using these values, we get the equation of refraction for a spherical surface. As we have derived this equation using proper sign convention, so this equation is valid for all cases. But you must remember to use the values of u, v and r with proper sign. For example, in the following cases, signs of u, v and r will be as shown. In general, position of a real object will always be negative, and position of a virtual object will always be positive. Position of a real image will always be positive, and position of a virtual image will always be negative. Note that for a spherical mirror, position of a real image is always negative, and position of a virtual image is always positive. This difference between the spherical mirrors and spherical surfaces is because in case of mirrors, the rays are reflected back and thus they actually meet on this side of mirror. But for refraction at spherical surfaces, the rays pass on to the other side of the surface and thus meet on the positive side of surface. Let us consider the ray diagrams to understand the properties of refraction at curved surface. When object is at infinity, rays close to the axis converge at a point. This is called the image focus of a spherical surface. When object is at a particular point, the rays after refraction become parallel to the axis. This is called the object focus of spherical surface. Note that we can have 4 combinations of the mediums and spherical surface, and for each of them the ray diagram will be different.